Hello Year 10. Today we're doing about transformers, and this will be the last lesson on the topic where you learn something new. After this we'll do a few consolidation tasks like the linking learning, the homework, the ARC, then the assessment, the test review, you know the deal. But here's the work folder for today. So let's go in there and let's go on to the PowerPoint. Right. What I'd like you to do is have a look at this video, because wireless electricity, or Witricity, was first proposed by someone called Nikola Tesla over 100 years ago, and he was a very clever man and predicted that it is possible. He just didn't quite have the technology available to him to be able to realize his imagination. So have a little watch of that video. You get a bit of Stephen Hawking's talking to you for a bit, and then a presenter tells you about the rest of it. Now, we do remember this, the national grid. So here's a spanner being heated with a very high current, which eventually causes it to melt and spark and lose energy through heating. So high current means energy lost because the particles heat up. Remember, we're talking about electrons moving through this object, and as they move through they collide with the atoms inside the object, which causes them to vibrate more, which causes them to heat up. So we're sort of linking a few different things together here. Now, high voltages. So that man was pretty safe where he was because he's not connected to ground, but you could see when he cuts that wire here, the voltage arcs back to this side, okay, and he's got a spring attached to this to pull it away. Or his friend, I think he's got another person that is attached to this, pulling this away. He is also safe again because they're in these buckets which are not connected to the ground. So the electricity is high voltage, so it can jump, and it wants to keep going to this path here. So that's why they've got two people doing it. It's very dangerous. We should remember this. Now, this should be, I don't know, embedded in your memory by now. So have a think, pause it if you forget, and then unpause it once you've had a guess. The voltage of the UK mains is 230 volts, and the frequency of the UK mains is 50 hertz. Okay, so this, you absolutely have to remember this. You don't have to remember this, but power stations generate 250,000 volts. Now, like on the previous slide, you saw what 50,000 volts does. Okay, it arcs, it's very dangerous, it can jump, and that's how you get a static shock. Is just a very small version of that. Now, that amount of voltage would be extremely dangerous in your houses, and it would just immediately arc to the walls or to stuff around it and cause fires. So, what do we have to do? We have to use transformers. Remember, we've learned about these before briefly at the end of the electricity part 2 module, but now we should understand why it happens a little bit more, because we've talked about magnetism and how a changing magnetic field induces a current, and the opposite, right? A current in a magnetic field can produce force. So here you got high voltage, 25,000 volts. Okay, the step-up transformer increases the voltage so that you reduce the current. Remember, power is always conserved. So let me just write a little quick something. Power is always conserved. So remember, P equals I times V. So this has to be the same. Whatever you do to this side, okay, say I increase this by 10 times, this must be decreased by 10 times. Because if you times something by 10 and then divide it by 10, you haven't done anything to the equation. So you can essentially change one value if the other one gets changed. So what happens is when you increase the voltage by a huge amount, the current will come down as well. So the reason why we're doing that is because we do not want to lose energy to heating. Now, when we get to the other end, the step-down transformers have to decrease the voltage so that it is safe for use. Because remember, high voltages are not safe for domestic use. They cause electric shocks, they could cause fires. But the high current is wasteful. So they wait until it gets near your house, and they step it back down to a safe voltage that you can use inside your house. Now, if you notice, the factories and the industry buildings, they use a higher voltage because they need that higher voltage to power their big machinery. Now, here, we should remember this equation, the power lost equation. So power lost, or P, equals I squared R. Just in case you can't remember that, which is one you need to remember, so we know that P equals I squared R, and the way you get this from is P equals I times V, but V equals I times R. These two equations are correct, but what we do essentially is instead of having a V, we know that V equals I times R, so you just replace that V, so you've got P equals I times R, and then P equals I squared R. And this is the power lost due to heating equation. Okay, so remember from the resistance topic that the heating effect in a resistor or a wire is proportional to the square of the current. That is just saying P is proportional to I squared. So for example, if a step-up transformer is used to make a potential difference 4 times bigger, the current would be 4 times smaller. Because the current is 4 times smaller, the energy lost would be 4 squared smaller, which is 16 times smaller. And that is why it's really useful to step up the voltage and step down the current. Right. So now we're linking everything together. We've looked at how a changing magnetic field can induce a current, or a voltage I should say, into a different coil. We know step up increases the potential difference, step down decreases the potential difference. The important bit here is it has to be alternating. So let's go on to the next slide and see why. This is a transformer. Now, in the previous lesson you saw we had a coil and I had a magnet that I pushed into the coil and it changed the voltage. Well, this time we've got this coil here creating the magnetic field. This coil is the one that is being essentially pushed through the magnetic field. Well, it's just a little bit different this time because they're both not moving, because when you have an alternating current, if you remember from the graph of alternating current, here is a graph of alternating current. You see the voltage goes up, it goes down to 0, it goes negative, it peaks again, it goes back down to 0, it goes positive. So all of the time the voltage is changing. Now if all of the time the voltage is changing, that means all of the time the current is changing. Because the current is constantly changing in this coil, the strength of the magnetic field around this coil is constantly changing. Now this coil is in a changing magnetic field which forces a potential difference across it. In this case, it is attached to a circuit, so it will make a current. And that is how these work. Now it has to be alternating current. So let's have a read through. 1. A primary voltage drives an alternating current through the primary coil. The primary coil current produces a changing magnetic field which changes as the current changes. The iron core increases the strength of the magnetic field. The changing magnetic field induces a changing potential difference in the secondary coil. The induced potential difference produces an alternating current in the external circuit. Now that is pretty much the whole process written scientifically in order. Notice that certain words have been bolded, like alternating current, changing magnetic field, which changes. Everything relies on the fact that the magnetic field changes all the time. We use an iron core because the iron core can be magnetized. Okay, and it increases the strength of that magnetic field. It kind of makes the transfer more efficient. So I'll leave you to have a read through that, make your notes on it, get your head around it, and pause it if you need to, but we're going on to the next slide. Okay, here's the equation that we looked at before. Vp, which is voltage across the primary, divided by voltage across the secondary, equals the number of turns across the primary, divided by the number of turns across the secondary. I find this one really easy to remember because there's loads of ways you can write it, but as long as you keep the voltages and the number of coils on the right side and the primary on the top or the secondary on the top, and the secondary on the bottom or the primary on the bottom, as long as you don't mix them up, you get it right. So I'm going to write this equation a few other ways that would be correct, and you can actually just rearrange this equation and find this out. So you could write Vp over Np equals Vs over Ns. Notice the voltages are on this, are both on top, and the turns are both on the bottom. The primaries are both on the same side. The secondaries are both on the same side. Okay. You could write it as Vs over Vp equals Ns over Np. These are all correct. If you rearrange your equation, you come out with the correct equation, but it just looks like it's in a different form. So as long as you remember, you need to figure out a way to remember this. I think it's one of the easiest ones to remember, but it is something that you do need to learn. Now, this is what 4 things mean. So you have to know that V is for voltage and N is for number of turns on that coil, and P stands for primary, S stands for secondary. So pause this if you need to copy anything down. Right. If, for example, the secondary coil has twice as many coils than the primary coil, the potential difference induced will be twice as big. If there is 10 times more coils, the potential difference will be 10 times bigger. This is how you use, this is the equation that you use to calculate whether it is a step-up transformer or a step-down transformer. So if you've got 10 times the number of turns of wire on the coil, on the secondary, this will be a step-up transformer, and it will step up the voltage by 10 times. So let's have a look. Let's do this practice question. I'll do it by hand, then so an AC power has a supply of a potential difference of 230. This is applied to a transformer with that many turns on the primary and this many turns on the secondary. So let's have a look. V primary, the voltage of the primary is 230 volts. When we don't know what the voltage on the secondary is, that's the question mark. They're asking us to calculate the potential difference across the secondary coil. They've said the number of turns on the primary equals 5,000. The number of turns on the secondary equals 250. Right, let's use our equation. So Vp over Vs equals Np over Ns. That's our equation. Because I'm trying to figure out what Vs is, I'm actually going to flip this whole thing. So remember I told you there's a little maths trick. If you just flip everything on the fractions, so put everything on the top that's on the bottom and everything that's on the bottom on the top. So Vs over Vp equals Ns over Np. These are both the same equations. You don't have to do this mathematical trick. It just makes it easier because I know I'm calculating this, so I don't have to then rearrange the whole thing. So let's put our numbers in. Well, we don't know what VS is. We're trying to figure that out. Voltage across the primary was 230. That equals the number of turns on the secondary we said was 250, and the number of turns on the primary we said was 5,000. Right, get my calculator. Right, so 250 divided by 5,000 equals, I'm going to write down here now, we've moved, excuse me, we have moved down to the bottom. Well, VS over 230 equals, and 250 divided by 5,000 equals 0.05. Well, I'm almost there. I need VS equals something, so I'm going to have to times both sides by 230 to cancel this 230 off. So if I times this side by 230, that cancels, and then times this side by 230. Let's see what we get. 230. So VS equals 11.5 volts. So the voltage across the secondary equals 11.5 volts. So this is a step-down transformer. Why is it a step-down transformer? Well, we started at 230 volts, and now we have moved to 11.5 volts. So we have stepped down. You would actually be able to answer question 2 without doing the calculation. Primary coil has 5,000 turns on it, and the secondary coil has less turns on it, so you know this is a step-down transformer. So I'm going to skip through the working because I've talked you through it already. There's a second equation. We know that power is conserved. I've talked about that before. So we know an equation, P equals I times V. Well, if power is conserved, you can say, using the equation P equals I times V, the power on the first coil is the same as the power on the second coil, so I times V, or V times I on the primary, must equal V times I on the secondary. So you're just using P on the IV. P equals IV. Now, again, V is voltage, I is current, P equals primary, S equals secondary. So we're just using equations that we already know, and we're using the rule that power is always conserved, because remember, power is the amount of energy you are transferring per second, and you can't just lose energy. You can't just get rid of energy. It has to be conserved. So we're just using P equals I times V, but P on the primary equals P on the secondary, so you can have I times V on the primary equals I times V on the secondary. What I'd like you to do is have a pause and have a try at this, or at least think about how you're going to do it. Then I'm going to work through. So have a pause, have a little go, see if you understand what's going on. If not, unpause it and watch my work through. Now, a step-down transformer is used to step down, well, we know it's a step down because I've said it twice, right? An alternating potential difference of 230 volts to 12 volts. Well, the voltage on the primary was 230 volts. The voltage on the secondary equals 12 volts. I know I always go on about how you should do this before you even start the question every single time. Now, it really is worth it, because all these words are confusing, but if you get the values out, you can just plug them in and then you get an answer. So it steps down to 12 volts to supply electricity to a 12 volt 2.5 amp lamp. Well, they've already mentioned the 12 volts, that's like a redundant information. Well, a current, so it's, hold on a second, so this is saying that the secondary current is 2.5 amps. Calculate the current in the primary coil. Okay, so they want us to calculate this. They're saying that assuming this is 100% efficient, that's very important because nothing is 100% efficient. what you'd do if it was not 100% efficient is work it out as if it was, and then use the efficiency equation to find out the real answer. They wouldn't do that normally, that's a bit cruel. So let's have a look. Well, I know that P equals IV. This is the equation that I can remember. Because this is 100% efficient, I know that P in the primary equals P in the secondary. Well, that means I can write I primary times V primary equals I secondary times V secondary. If you just prefer to remember this equation, that's fine. I've always told you I don't have a good memory. I remember a few equations and I apply them to the situation, which I think helps with my understanding of physics. Well, let's put the numbers in. IP, we don't know what IP is. I'm going to leave that as IP. Times by times by VP. So what's voltage on the primary? That's 230, which equals IS. What's the current across the secondary? It's 2.5 times by the voltage across the secondary, which was 12. So again, I'm just going to get my calculator. 2.5 times 12 equals 30. So I have got IP times by 230 equals 30. Now I need IP by itself, so I've got to divide both sides by 230. And this cancels with that. And then 30 divided by 230 equals a horrible number. IP equals 0.130 amps. We'll leave it at that. Okay. If you are comfortable with rearranging equations, so I'm just going to put a little side note. You know that you are trying to calculate IP equals something. If you are comfortable with rearranging equations like this, you can straight away go IP equals ISVS divided by VP. If you are not comfortable with rearranging equations and it's easier to work with numbers, you put the numbers in first. Both methods are correct. Both get you all the marks. One is easier just depending on how you think. Okay, let's move on. There's the solution. And you can see I got it right. Good for me. Here are two transformers. This is what they look like. Notice the primary coil. Usually when you are given a diagram, the primary coil will be on the left and it should be labelled. Now, here's another one. So this one here, look, this is a step down transformer. Notice there are lots of turns of wire on the coil on the left, and there are less turns of wire on the coil on the right. So on the primary coil, I'll rephrase that. On the secondary coil, you have got less turns, so you would have less voltage. This one here, the secondary coil, has more turns of wire on the coil. Because you've got more turns, the voltage would be increased, so this is a step up. That is the easiest way to spot a step up transformer versus a step down transformer. So we're going to do some questions. I'm going to get rid of this. So here are the exam questions that I'd like to have a go at. What I'll say is, have a go at the exam questions. I'm actually going to go through and do them and show you the answer and explain why. So it would benefit you to have a go at the questions and then mark them. If you just want to have a go at them and mark them using the mark scheme at the end, that is fine. Because you're a triple class, I trust you to have a go and then mark afterwards. Right, question 1. So what I'll say actually, again, pause the video, come back to it later, do your questions. Maybe you could do question 1, then mark it, then do question 2, pause the video, do question 2, then mark it, unpause it. Okay, you get the idea. Right. The transformer made by the student would not have worked if the iron core if the core had been made out of aluminium and not iron. Why? Aluminium cannot be magnetized. Not be magnetized. Magnetized. You would have also got the mark if you said aluminium is not magnetic. Only a magnetic material works as a core, and we use iron because you can make it very soft, so it's very magnetically soft, which means that it's easy to align all of those domains up and create a magnetic field. B. The student made changes to the number of turns used to make the secondary coil. He then measured the potential difference across the secondary coil after each change. The graph shows the student's results. What range was used for the number of turns on the secondary coil? Okay. So what range did he actually use in his experiment? So he's plotted from 0 to 50, but did he do the experiment from 0 to 50? You have to look at his results. Well, his first result is this one here, which is at 10. So that first result is from 10, isn't it? Now, what was the last result he did? Well, he did one at 20, 30, 40, and he did one at 50. So the last result is 50. So there isn't a reading at 0. He didn't do a reading at 0. So that is not included in his range of values. When he drew a line of best fit, the student ignored one of the data points. So he's ignored this one here. Why? The word you use is anomalous. Let's see if I can spell it. L-O-U-S. That is an anomalous result. If you're going to put it in English, you just say it does not fit the pattern. This point does not fit the pattern that the rest of them are following. It is anomalous. This is the word, this is the key word that you need to know. What is the minimum number of turns on the secondary coil for the transformer to act as a step-up transformer? Well, let's have a look. Well, the power supply, or the voltage I should say, across the primary coil was 2 volts. So for this to be a step-up transformer, you would have to have an output voltage of more than 2 volts. So let's have a look at this graph. Well, there's 2 volts, okay. There's 2 volts. Don't do that. There we go. So if I had 20 turns of wire on the secondary coil, I would have exactly 2 volts. So for this to be a step-up transformer, I'd need to have more than that. So I'm just going to pick 21 turns. Why? Because, well, the output voltage or the secondary voltage is higher than the primary. Or you could say something like the output is more than 2 volts. So, a radio can be used with a 9-volt battery, or it can be plugged into the 230 volts mains. Electricity supply using it can be plugged into the 230 volt mains electricity supply using an adapter. The mains adapter contains a transformer. Why must the mains adapter contain a transformer? Well, you have to step down the voltage. 230 volts going through something like this could damage it. It's just a small appliance. It doesn't need very much voltage. So I'm just going to say, why must the mains adapter contain a transformer? Well, you need to step down the voltage. That's it. So, question 2 shows the construction of a simple transformer. The student makes 3 simple transformers, J, K, and L. And here they are on the graph. Figure 2 shows how the potential difference across the secondary coil of each transformer varies as the potential difference across the primary coil of each transformer is changed. So you can see here, they've changed the voltage across the primary coil, and they wanted to have a look at how the voltage across the secondary coil is changed. How can you tell that transformer J is a step-down transformer? Well, remember that a step-down transformer, the voltage across the primary must be greater than the voltage across the secondary. So let's have a look. I can read this value here a bit easier than the others, so I'm just going to read that one. There's my value. Well, the voltage across the secondary is, sorry, that's the primary. The voltage across the primary is 6 volts, and the voltage across the secondary is 4 volts. So, well, that's definitely a step-down transformer, isn't it? The secondary voltage is smaller than the primary voltage. So how can you tell that J is a step-down transformer? Well, Vs is smaller than the primary voltage. And I'm just going to put Vp. Each of the transformers has 50 turns on the primary coil. Calculate the number of turns on the secondary coil of transformer L. Okay, so they've asked me to calculate the number of turns, and we've got voltage, and we've got turns of wire, so I know I need to use Vp over Vs equals Np over Ns. So let me write down my values, because it's quite a long way to scroll. Right. Vp, Vs, Np, Ns. They have said primary coil number of turns is 50. Okay, good. They've asked me to do transformer L. Well, the potential difference across the primary coil in L was 6. I've just picked that value because it's the easiest to read. I've picked this value right at the top here. Well, it's 6. And the the voltage across the secondary coil is 12. Okay. I can already see, just because I know the equation, you have to put it in and work it out. I can already see, because the voltage has doubled, the number of coils, the number of turns of wire on the coil will also be doubled. Let's prove that. So let's put our values in. Vp is 6, Vs is 12, equals number of turns on the primary is 50, number of turns on the secondary is we don't know, Ns. Well, what's 6 over 12? 6 divided by 12 is 0.5 equals 50 divided by number of turns on the secondary. Now I need to get number of turns equal, so I'm going to times both sides by number of turns. Yep, so this cancels with that. So I'm left with number of turns on the secondary times by 0.5 equals 50. Now I need to divide both sides by half to get rid of the 0.5. Divided by 0.5, so that cancels with that. Number of turns on the secondary equals 50 divided by half. You can put it in your calculator, but 50 divided by half is the same as timesing by 2, because it's saying how many halves go into 50. Well, 2 halves go into 1. Okay, so 100 halves go into 50. Number of turns on the secondary, and yes, it is double. Question 3. Batteries inside a laptop are charged using laptop chargers. It contains a traditional transformer. So that is a traditional transformer, and it's giving you an inside view. Explain. So the alternating current flowing through the primary coil of the transformer creates an alternating current in the secondary coil. Explain how. Right. The first thing you need to say. Always need to say the alternating current creates a changing magnetic field. Okay, so AC creates a changing magnetic field. Now, if this is a 6 marker, you'd probably get a mark for 1 mark for changing, 1 mark for magnetic field. So the iron core links it to the secondary oil, kind of. So the way you would say that is the alternating current creates a changing magnetic field in the iron core, because the iron core kind of delivers the magnetic field to the secondary core without it getting wasted, essentially. Some of it is wasted, but the iron core makes it really efficient. What does that then do? Well, this causing an alternating potential difference in the secondary core. We have to use the special word, causing an alternating potential difference to be induced. Okay, causing an induced alternating potential difference, or causing an alternating potential difference to be induced. That's a really important word. You've got to write that in the secondary coil. And that, for 3 marks, is it. Right, use the information from the diagram to calculate the potential difference the charger supplies to the laptop. Okay, I'm going to scroll up a bit so I can write my stuff down, because this is asking me to calculate. I need to calculate the voltage induced into the laptop. So what that's saying is calculate the secondary voltage. Because I'm giving loads of information here. I'm given a current, I'm given voltage, I'm given number of turns on the coil. So I'm going to start with that. So primary, so number of turns on the primary equals 575. Number of turns on the secondary equals 50. Straight away you can see this is a step down transformer. The main supply, so the voltage on the primary equals 230 volts. And the voltage on the secondary equals question mark. That's what we've got to calculate. We are also given a current. I'm going to write that down anyway. So we are given a current, and that is on the secondary because that is going to the laptop, and we're given 3.45 amps. I'm going to tell you we don't need that bit of information yet, but we will need it later, but it's good to write it down. Well, if you look at these here, you should see that we can use this equation. So voltage of the secondary equals divided by voltage over the primary equals number of turns of the secondary over number of turns of the primary. Let's put my values in. Well, that's still voltage of the secondary. We don't know, it's a question mark. 230 equals number of turns on the secondary, which is 50, and the number of turns on the primary, which is 575. So let me get my calculator out. 50 divided by 575 equals a horrible number. So Vs over 230 equals 0.8696 ... and it goes on for a long time because it's a recurring number. Now I'm going to times that by 230, because if I times it by 230 I get, so I'm just going to put a line under here. So we're now here, so Vs, if I times this by 230, the 230 cancels, and then I times this side by 230. So times 230, I get my answer is, that comes out as a nice number, equals 20 volts. So there we go, my potential distance is 20 volts. I'm going to change my color now because I'm moving on to a separate question. I don't want it to get confusing. Part 2. Calculate the current in the primary coil. Oh, well, they want me to calculate this now. We've got our answer for this one. We've got that as 20 volts. So calculate our current in the primary coil of the transformer when the laptop is being charged. Assume it is 100% efficient. When they say this, you should have a little, whenever they say assume the transformer is 100% efficient, you're thinking, hold on, power wasted due to current. We've got a power equation here. Well, this is the information they've given me, right? They've given me a current, they've given me a voltage. I know power is P equals I times V. Now let's have a look. Well, power is always conserved, so I in the primary times voltage in the primary equals I in the secondary times voltage in the secondary. Let's put our numbers in. What's the current in the primary? We don't know. We need to figure that out. Voltage in the primary is 230. Current in the secondary, we were given at 3.45 times by the voltage in the secondary, which we just calculated was 20. Let's have a look. What's 3.45 times 20? That's 69. So IP times 230 equals 69. Now I need IP equals, so I've got to divide this side by 230, which gets them two to cancel, but I've got to do the same to this side too. 230. So 69 divided by 230, that is 3/10, which is 0.3. So the current in the primary equals 0.3 amps. So there it is, 0.3 amps. Last question. Laptop and mobile phone batteries can only be recharged a limited number of times. After this, the batteries cannot store enough charge to be useful. Scientists developing new batteries that can be recharged many more times suggest one advantage of this. Well, think of any kind of obvious advantage. If you're not throwing away phone batteries, or in this case, because you can't detach your phone from the battery, you're not throwing away phones as often. So there's less batteries going to landfill. So there's less energy wasted because they'll be more efficient. Less pollution making new batteries, I suppose. So let's pick one. I like less waste batteries. Unfortunately, waste batteries can't really be recycled, so where do they go? They go to landfill. In landfill. And there we are done. So hopefully that was helpful for you. Please email me your notes and your work, and then that's everything done.